Hi everyone, welcome to uh, the quantum session, Grover's algorithm review. So what we did last time, so we know that this is September 4 session. I have to call it 13-14 because 13th we had left part of it, and this is Labor Day, and what we had envisaged prior to this. So what I will say is September 4, our recording did not happen properly, so I had to redo it. So I'm just reviewing that we had completed what you call the first part of the Grover search algorithm, and that was at the 13. And then we just a quick review is that we had completed the implementation of, or rather, we had looked at the logic about creating the quantum phase circuit UF along with a uh, Hadamard followed by a universal UFV gate followed by a repetitive or UV and VW repetition where W was your what you call the diffusion algorithm. So what I'll do is since we have a bit of a disconnect, so I will start with the uh, summary that last time what we had done a, if you go to your exercise on the session 13 1, you will find a rotation of 5, and that rotation of 5 is the vector. Three vectors were there: 5 vector, the a vector, and the a perpendicular vector. A perpendicular and a are perpendicular to each other, whereas phi is just at an angle theta with respect to a perpendicular. And then what we did, the operation of reflecting the uh, phi with respect to the a perpendicular, we did it to bring it a reflector, so a theta angle it went clockwise, and then we rotated the phi which v which was moved to the bottom, and that is below the uh, a perpendicular. We rotated it uh, twice the theta so that we pivoted around the phi itself, the v, and so we got a 2 theta and we called that w. So we did the wv operation a number of times to, and that repetition depends on the how many qubits are there and how different is your search, how big is your search space, 2 to the power n, or if you call it 2 to the power n equal to lower n equal to capital N, then we say our search space was n, and so we try to ensure that we are able to get that rotated with a transformation WV repeatedly to move it 2 theta every time, VW, VW this way, and the answer can be depending on the how many rotation we do. The maximum rotation is square root of n. Normally, if n is the space, square root of n is what we can achieve with. It's called quadratic gain we can get out of Grover's algorithm. Even though it's a not exponential, as we would say, it's quadratic, but that's the limit. And so we'll just go with the Grover's algorithm portion today, because next session is recorded separately, which was on September uh, 11. So what I will do is, this is session 13-14 kind of a thing. 15 will be in the next one. So we only focus on the 13-14 here. And so we have seen Grover's review. Let's start with a numerical example to understand the Grover's algorithm. That will be the easiest way. So assume you have a database of 4 indexes to search to target one winner index. So that should be index. Okay, we'll fix that. So the entries are 0, 1, 2, 3. So obviously we are taking 2 to the power n equal to 2 to the power 2. So there are 2 qubits to search, and we are trying to locate entries 0, 1, 2, 3, and our winner is assuming 1. This is to simplify the understanding. So to reach 1, what we need to do? So normally if you have a database and or any unstructured data, and if you have entries in a string 0, 1, 2, 3, and then you start looking from, and we don't know whether they are in order. Assumption here is it may not be in the order. It may be 3, 2, 1, 0, 0, 1, 2, 3, whatever the index is. But when we search through the entries, assuming that this is the order, it can be any random order, because we don't know how things are organized. They are not ordered. The search, when you have a n space, you don't know what is where. You don't sort. You just do normal classical search, and when you do a search, you compare one by one all the n. So the order of the worst case use is you will get n searches to identify one. In this case, we are saying we will be able to get it in square root of n. And to do that, the entries we have 0, 1, 2, 3, and 2 to the power 2 is equal to, so just a 4 element, so it is easy to understand. To reach the we need the winner a equal to 1. Further, there is a phase quantum oracle. So we discussed last time how to generate a phase quantum oracle UF. There is a formula which we applied, and that formula is available to us, but we'll go with the flow right now. This all vectors, so we have to talk about three. One is the vector phi, which is linear combination of all the catex. In this case, the catex can be ket0, ket1, ket2, ket3, and that's what is reflected here. And you have, if you have n by 2 element, then obviously 0 to 2 raised to n minus 1, because we are starting with 0. So basically, 1 by the average, of course, we have to take the what you call the magnitude has to be normalized. So we put 1 upon 2 raised to n by 2 sigma x0 to 2 raised to n minus 1 ktex. And if you act, this is the general phi vector. And when you take a 0, 1, 2, 3, they are represented as binary here. It may be represented as decimal. But all it means is when you do n is equal to 2, 2 by 2 is 1, so it will be half. So every combination 0, 0, 0, 1, 1, 0, 1, 1, both qubits have half half, are, because there are 4 elements, we have a probability of 1 by 2 for each one of them. Obviously they are a 0, 0, 0, 1, 1, 0, 1, 1, so 2 qubit combination. Now if we had example, we take that we don't want the element which is our victorious, which is what our target element is 1. So if you remove 1 from this, that's what we get in a perpendicular. So a, our a which is there, target is 1. So ket 1 or ket 0, 1, a is equal to, our a ket is equal to 0, 1, which is our target. And so the phi vector contains 4, the a vector contains 1 element of the 4, and the a perpendicular contains the remaining 3, which is 0, 0, 1, 0, and 1, 1. 0, 1 is eliminated because that is our target. So when we have a space, search for space, search space of 4, 2 to the power, that is 3 of them is included in the a perpendicular, one of them which is target is in one of them, and a perpendicular are orthogonal, so therefore they are perpendicular in this case if you show on a xy plane or a simple straight plane. And then whereas our phi vector contains everything, so you need 3 to search. To solve a Grover's algorithm, you need 3 vectors. One is the phi vector, one is the a vector which is our target, and phi other than the a which is our a perpendicular. So these are the 3 vectors which we generally require. And the construction of quantum now comes. So we know what the input is. As we saw, all 4 entries will be, strings will be passed through the oracle, which is nothing a black box. and then at the end of it, we will do some operation on that that will result in the reaching this result as 1. So it may, if it is a 321 3201, then 3 2 is not matching, 1 will match, so third one. So it could be in third 3, uh, every time you do some operation on the black box, which is nothing but your transformer, that is the unitary transformer plus some circuit combination. So that is the oracle. Oracle is the black box. So when you apply to the black box the operations, so we had looked at the operation last time, that how do you generate oracle. So there were two types of we could do. One is the phase, um, and the other one is the phase. One was based on the phase split, or a, uh, so we call it as phase quantum, phase shift quantum, and the other one we had a C naught, or C exclusive or phantom, C exclusive or quantum. So we could do with two possibilities. And so when you do a oracle design, you take the I equal to 0 to n minus 1, j equal to n minus 1 of the uh, projection of I on j or j on I, whichever way you choose to call it. But either way, it's like you can say uh, this is bra j ket j. Bra j ket j will do what? It is equal to bra j ket j when you have it's equal to 1. Same way, bra I and ket I, if you take these two, this will be 1. So basically, we are just saying that u equal to u, but with I and j running operation. So if you look from the structure, see, because we do not know the structure, what is the structure of the uh, construction of quantum oracle uh, will not provide us how the oracle is available. Let me just check if everything is being recorded, just to ensure that we are on the recording. Yes, it is recording. Thank you. So I'll go back. So what we have is the construction of u f, which is the function which we want, and the matrix. Obviously, the matrix is how what matters, and in this case, our target is 0 1. So 0 1. So you are having a this portion which is 0 0 0 1 1 0 1 1. If you take, so this is the place where we need to have a minus 1. And so what we are doing is we are trying to build a quantum oracle whereby you have a function. This is the function we need to be able to achieve what we want. Plus, at the same time, we know 0 0 is represented as this, 0 1 is this, 1 0 is this. So basically, you can write down as is, but except that 0 1 needs to be negative, because you remember we said that when we move the vector phi, which is linear combination, all of them, and then reflect on that the a perpendicular, which is nothing, linear combination of the three of them, this one 1 by root 3, then it needs to be reflected. So the first is phi is reflected with respect to a perpendicular, so it will go down by theta. Once it goes down by theta, that is our v. So this is v, which is xn, which is minus 1 raised to fx xn. So in this case, if we get our target as a, then this should be minus. So that is why it corresponds to this. So our v, which is our uh, vector which we are trying to move around the a perpendicular, so we get a v by taking the phi, that is phi is our linear combination of everything. Out of the everything, the one, if it is hits a, which is what we are looking for, then we need to get a minus. So that means that is the one which is separated out from the others, rest of them. So you remember that when you have a 4, uh, the mean is different. When you have 3, the mean is different. So that itself will give you a difference of one third to one half. So essentially, because of this, we know that we have already the average is different. When your average differs, then you know the gap, and the gap is represented in terms of theta in this case. Uh, so we reflect around a perpendicular, as you know in the diagram we had seen last time. So essentially what we are doing is we are taking 0, 0, 0, 1, 1, 0 and then constructing a particular UF. Like example, we take a UF 0, 1. So if you put a 0, 1 in this way, get 0, 0, 1, get 1, get 1, get 0, get 0, get, and U remains as it is. So ultimately, except when it is 0, 1, you will get a minus 0, 1. If you do a UF of 0, 1, then you will get a minus 1. If you do a 0, 0, you will get 0, 0. If you get 1, 0, you'll get 1, 0. 1, 1, 1. So basically what it means is there is no change unless it is the target which we are looking for. So this is nothing but using this uh, U and then calculating V equal to UF, and so this is V. So that means UF uh, looks like a control Z gate, and CZ or control phase shift gate, phase shifting being pi. That is what we are doing, and so we can look at this, and this is how it will look. So you got a UF, because we said that we are using a control Z or control X, whichever. In this case we are using U naught. So if your U naught is, UF is existing, UF is unity, right? There is nothing in that. It's just a we perform a NOT operation on the MS bit first. So you got a LS bit and MS bit too, because we have only 2 qubit. So we have a 0, 0, and so first is kit 0 and second is kit 1. Okay. So kit 0, kit 1, this is your Q0, this is the Q0, and this is Q1. So Q0 can be in the state kit 0, kit 1. Q1 can be in the state uh, kit 0, kit 1, but in the initial they are all 0. So we are saying that both are 0, and then you do Hadamard, and since you are doing a double Hadamard on both of them, so that is why either you can write a Hadamard 1 here, Hadamard 1 here, or combine these two and then say you have created a Hadamard of two Hadamard gates are applied each on the individual Q0 and Q1, that is the LS bit and MS bit, and then you generate a phi, because we said that we had looked at, right? We had said that you have all four, and then 1, 2, 3, 4. All of these four are linear combination is generated. That is phi. So this is how the phi is generated. So your phi is generated based on the Q0 Q1 combination and with a Hadamard operation. So you are getting a linear combination of all 0, 0, 0, 1, 1, 0, 1, 1 on the Q0 and Q1, which are nothing but states, can be basis states, can be 0, 1, 0, 1, and that's why you get a MS bit phi. So phi is generated by doing a Hadamard on the Q0 and Q1 bits, Q0 being LSB, Q1 being MSB. Now you generate a phi. So once you have generated a phi, what is our next operation? So uh, next is UF. So that means this is the U, which is UF is nothing but V, we said, and this is W. So we have got a circuit, sequence of circuit where we have to do a linear combination to generate phi. Then the second operation we have to generate a V, and the V is generated how? So UF is defined as U naught. This is tensor operation. So U naught of I. So and then uh, this is the uh, so you got a CPS, control phase shift. So after doing a U naught on I, you do a control phase shift and by pi, and then you apply a U naught I. So U naught I are nothing but they are just a uh, X. Basically, uh, not gate is X. So you have a X and you have a I. So our UF, you know, our what do you call the constructor for the Oracle for UF is U naught I. In between you are doing a phase shift. So this is equal to having on the Q bit. Uh, so this is MS bit, this is LS bit. So LS bit is I, so you got a I, and you got a U naught, which is nothing X. Same way Z is nothing but control phase shift. Now control is by MS bit. MS bit controls the phase shift of the uh, what you call the LS bit. So this is a kind of a C naught operation, right? Sorry, control phase shift, which is XOR based on control naught, we call it. So if it is zero, then you get a no change. If you get a one, then it flips. So that is the operation. So you can see that UF operation is V, UF equal to V, which is nothing but a C naught or a C naught on the MS bit, which is X, uh, not C naught, but X, not U naught, that is unitary negate. Not usually not gates, we don't have to worry. It's obviously a 0 goes to a 1, 1 goes to a 0, and that means it is reversible. So anytime we put a not, it should not affect our universality, that is reversibility. So once you put a X, and then you are saying that you are doing a tensor operation with I, so X tensor operation with Y with a uh, control phase shift of pi with a Z gate, and followed by a same U naught I. So this is our oracle for generating from phi the V vector. What is the V vector? All V vector does is it takes the, we know that it's a 8, whatever you have got phi, you are trying to reflect it around phi. So around the phi, we have a UF which is reflecting around phi to generate the theta angle. And that theta angle is what we use to do a 2 theta on this operation. So twice the operation we do to get a 2 theta on this, and this is the repeat operation we need. So this generates your V vector. And now go to the Grover's diffusion operator. To generate W, what we do Hadamard of both. So whatever output comes out of this, we just do a linear combination thereof to get them again back to your 0, 1 combinations. That is a standard basis we get them. Here we applied for generating the what you call the superposition, and then here we are getting whatever we are getting, we are trying to make sure that we are in the we are also getting in the operation in a way whereby we can apply the double W operation. So for W operation, what we have is Hadamard on this side, Hadamard on this side, which is 2, and then we are, what we are saying is we are having a phase. So what we have done is we have done a control phase shift here. Same way we do a control phase shift, but after doing a what you call the phase shift on both of this. So what we have done here is we take a Hada mod and we get 0, 1 basis, and then apply again the the phase shift or the Z operation. So both of them we do a Z operation, again do a control phase shift of pi. So basically we are able to get through this, the rotation. We'll look into the detail in the following slides. But at the end of it, we should get a the selection, which is after doing repeated operation. Okay, this is not single operation. This to VW may be repeated n number of time till the it reaches 5 to V, VW, 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 a number of time, depending on, it could be up to root n times, depending on the number of, in this case, we have 4. So if I take a root of 4, it should not be no more than 2 operation. So 1 operation, 2 operation, if we do, we should be able to hit our target, which is ket A, or in ket A is in this case 0, ket 01. So this is the entire construction of a diffusion operator. This is the diffusion operator part. This is the uh, unitary operation part of it. So unitary plus the diffusion. So basically, target is differentiated based on the averages. As I mentioned, the average being 1 by root 3 and 1 by 2. So what happens is, if you have 4, what is the average? If it is 1 by root 3, what is the average? And then that differential can be expanded until we know that we have reached our target of hitting the A, which is not included here, which is included here, right? So basically, we are distinguishing, amplifying, inversing, amplifying, and then getting the output out of it. That's what we are doing. And we can prove this. So you can see that if I have a UF, if I do this example operation, we had shown UF operation, which is V operation, this can be shown by U0 is nothing but your X is 0110, and if you do a I is 1, this is 1001, which is identity matrix. So if you multiply this, and if you multiply all these, at the end of it we get this one, which is what is showing that by doing a V operation, or the UF, or the operation of uh, a C U naught with a CPS with a U naught. Uh, that means what? A C naught operation on the two uh, qubits with a control phase shift by pi, following that, and following that again a U naught operation with respect to the two qubits. We end up in a UF, which is our V, where we know that we have identified at least uh, the candidate which is likely to succeed, and this candidate can be further taken down on the diffusion operation. When you apply the diffusion operator, you are just taking those inputs which we got and doing a Hadamard on both sides. N number depends on, if your qubit is, we have got only 2 qubits, so only we'll have 2 Hadamard gates on both sides, and with a twice the operation on whatever our uh, uh, winning candidate we are likely to see. Uh, in this case, it will be uh, 0, 2. So we are doing that, and this is how it will be. So you can see Hadamard 2 is nothing, 1 by root 2 1 minus. This is 1 by root 2 1 minus 1. If you do this, you are going to get this, and this is what is going to be applied. Hadamard is being applied to the. This is the circuit which we got, and for that, from that we can derive the W operation here, and they say 0202 minus 1 is nothing but 100. So basically 02 is our, so you remember that 00 is our first one, and the second one is 100. So if you have 02, so we have 100 row matrix and column matrix, and minus the identity matrix. So if we do this, we can see what we can get. Here you get a 2, and here you get a 1, and when you subtract all this, so basically this is what is our circuit. So essentially, we are trying to say that 2O2 ket. So this is where the ket O2 and bra O2, twice of that minus 1. So basically 2 theta is what our operation is. And then once we do a theta, that is nothing but z. This is equivalent of z. Uh, so what you see is that control phase shift operation by pi with a z, with tensor z. That's what you have seen in the circuit, and so that is what we are doing. So basically both side is Hadamard, and then you are getting a control phase shift z on the operation of the 2 theta which we are trying to, phase shift by pi which we are trying to get. and this is what exactly turns out to be. And we can do mathematically through matrix as we see here, as well as we can do through circuit. Ultimately, construction of the Grover diffusion operator is shown by here using the U, that is, this is the control phase shift. So you got a UF of, that is unitary control phase shift by pi z by z, and this is what it is, same thing. So we are just trying to compute through matrix or through circuits. Ultimately we are ending in the same thing. So essentially, here we can say that if we have a 2 qubit with a 0 with a 0 0, then you got 1 0 0 0 at the far left, because we are talking about the operation here uh, of Hadamard with a 2 qubit 0 0. And what does it give you? So when you do a Hadamard, it gives you the, already we have computed this previously, you can see here we have computed what is 202 minus I. This is the matrix. So the uh, how we can take a 202 operation, which is the W part of it, and then apply the 1000 matrix on it. So essentially, we'll end up with this formulation, this row column, row column, row column, and this is the only one which is valid. All these are zeroed out, so all these three multiplication will go away. So we'll get only 1 1, half of it. So half of 1 1 1 1, and this is nothing but equivalent of our generation of half with all combinations 0 0 0 1 1 0 1 1. So this is the one matrix multiplication which shows that the wave function initialized, and we get this. And the wave function, we can also take a v phi on this. So we have generated a phi here, and then after generating phi, we are applying the UF on that, and then we are getting, it is clear that ket A equal to 0 1 while keeping other basis vector intact. So without changing the other basis vector, we are just trying to amplify the one which we need, and that's what you are getting, 1 1 1 1. So all the diagonal elements are picked up. So 1 minus 1 1 and 1. So diagonal matrix is picked up, and half, which is the average, it is remaining. So UF of half into all this is ultimately boiling down to V into phi. So we saw the phi earlier. This was our phi, and this is our V phi. Uh, and so essentially, we have three, as we said. First is the um, W. This is the W part of it. We had the uh, V. In this case, this is W part of it again, and this was the uh, W part with Hadamard on sides, so that we can change the basis states to ket 0, ket 1, and that's why you got the multiplication of this at the end as well as beginning. And so we turn out to what we want, and this is the overall picture. If you go into because this is for a 2 qubit with 4 by 4 matrix, you can see that the whole matrix operation looks complex, but at the same time it's simply turning the uh, amplification on the target A search, which we have the string search 0 1, which is what out of the four binary input which are mapped, and only two finally we get, and those two is nothing but 0 1 in this case. And this is what we can also look at in terms of cos theta, uh, same thing but with a matrix. Instead of matrix, we can also use the function cos theta. Like example, cos theta is a perpendicular phi. So what you have is the uh, the angle which we saw last time, and I should have kept the figure here. Anyway, I have the figure here or not? Okay, figure is not here. But last time we had seen the combination. So So as usual, our three pictures are important. One is the A, which is perpendicular, which is vertical. A perpendicular, which is along the x-axis, and phi, which is just theta above the uh, x-axis. So when you take a cos theta is projection of phi on the uh, A perpendicular, and that is what we are computing here. We know that this is the 0, 0, this is the 3, this includes the 3, this includes the 4, and when you do a 1 by root 3 into 1 by root 2, this is what we had already calculated previously. Here it is. Yeah, here it is. So we had defined phi and we had defined a perpendicular, get a perpendicular, and what we are doing is just multiplying them. So you are taking the uh, a perpendicular and a phi, and then you multiply. It turns out to be root 3 by 2. And when you say root 3 by 2, this therefore this is equal to pi by 6. If you do a cos theta, cos of pi by 6 is root. So therefore, our W operation will rotate 2 theta, that is 2 into root 3 by 2, which is 2 into pi by 6. So it will be pi by 3. So it will be aligned with A ket A. This should be ket A because ket A, it rotates pi by 6 to start with, plus pi by 3, and you can see the circuit that this rotation pi by 3, so pi by 3, pi radian is 180 degree, 3 is 60 degree. So if you take a 60-degree shift in one time, you really don't need second repeat. So what it means that because of the closeness of this 3 and 4 being just 60 degree and 90 degree, if you do double 60, then it will go actually exceed. You will not need more than one rotation. Essentially, that's what it turns out. So if you look at the circuit, we can see that we can implement XOR with just one rotation. Although computation wise, we may think that it will go, but if you do 60 plus 60, then it will go 120. So we don't want overshoot. We just have to be closest, and that's all. So we have been assuming that quantum oracle is given as a phase oracle. So this is based on the phase shift. Z gates, what we do, Z gate just it does a phase shift. So this is a phase oracle implementation. There can be a other implementation also. So this is a phase oracle implementation of W, and with Hadamard all the time. Hadamard is required because every time you have to measure in unit basis. This is you Ket 0, Ket 1 basis. So we can also try a different method in this case. And that method is in this case what? Quantum oracle using phase oracle we did. Same way we can do a XOR quantum oracle. So you have two ways of implementing. As we did in Daishosa algorithm, same thing applies to, in this case, our Grover's algorithm. Here also we saw previously what was the uh, implementation called phase oracle implementation. In the phase oracle, we use the Z gates. As you saw, we have all over spread only Z gates and the NOT gates. But we have not used any Hadamard, identity, phase shift gates, and NOT gates we have used. But nowhere we have used a C NOT gate. Okay, so these are XOR gate, what we call. So in this case, we will come back here and look at growers and how can we using XOR quantum oracle. So the two types of oracles you studied previously, we applied for the Deutsch, same thing we apply for the what you call our growers. And in the growers, we have taken the simplest example. Even with one WV, we are able to get it. But that being said, that was based on the Z gate. And similarly, we can, that is Z, that is the phase shift or phase flip. So phase flip gate is your Z gate, which is what we applied. In this case, we can also use XOR to generate. To incorporate XOR, it should be part of the V. Like part of the XOR, part of the V in that case was Z. So we can go back and look at it. Our Z was part of the V. So you can see here part of V and then W. So similarly, we can, instead of Z, we can apply a XOR here. So how do we get XOR combination? That's what our goal is. So what we do is here, so what we can do first, XOR quantum oracle is a, so remember that in the case of phase flip gate, um, we just have uh, the 2 qubit inputs. There are no extra gates required. But in the case of XOR implementation, you will find that you got 2 qubits, and then you may need additional gates, because in this case, uh, 2 plus 2 plus 1, 5. So essentially, when you do XOR implementation, you have to map n plus m. So n in this case is 2 to the power uh, 2, which is 4. So we'll require additional uh, what you call a qubit. So we can add additional qubit, or if you are able to use ancillary or whatever we call, that should be sufficient. So the mapping matters, because you map n to n or n to m or n to 1. So if you have 2 qubits and you are mapping to 1 qubit, then you can do it on the LS bit. Uh, but if you do have, so MS bit becomes the control bit, and uh, the LSB portion of the qubit, there is Q0, Q1. Q0 becomes your measurement point. So we have to apply input to n, measure on m. So therefore it is n plus m. Therefore the operator will be n plus m into n plus m. That's what here. Uh, so obviously x, when you say fx is your output, it can be either 0 or 1. So we only need 1 qubit, thus m equal to 1, refer to u f x y equal to xn yn yrf. So you remember that our unitary operation for the XOR quantum is that our y is a function of x, which is nothing y exclusive or f of x, where f of x can be 0 or a 1, and that's why, therefore we have n plus 1 qubits are required in order to use, which is what we mentioned. So if you have 2 to the power 2 4, then you need a 3 qubit. For a 2 3 by 3, then in that case 2 into power 2 to the power of 3, that means it will be 8 by 2 4 8. So it will 8 by 8 matrix. Obviously, depending on how we do it, uh, the one n plus m is required. So in this case, we have taken LSB m equal to 1 and MSB n. So essentially what happens is we have taken n qubits here, and m is your output. So your measurement will be done at the m part of it. So what we have done is, here we take a circuit based on this formulation. So what have we done in this formulation? We have done minus. So when we say minus, how do you obtain minus? If you have a bit and which is initialized, and if you do a inversion, that is, you apply a NOT operation on it and do a Hadamard, you can generate a, this is a qubit, right? Qubit means it may be uh, a 0001 at least, or 0001 1011. So when you get this linear combination of that, and if you are doing a negate, that means you are getting a minus. If you had not done a negate, you would have got a plus. So basically we are generating a minus and applying that minus to the V vector.